Hello student, today we will start learning theoretical computer science, which is the second paper for TY computer science. Basically, theoretical computer science is used for compiler construction. It is also useful in many other areas such as language processing, operating system design, machine learning, computational geometry, and many other areas. Now we will discuss the syllabus of this paper. The main application used for this theoretical computer science in our subject is compiler construction. It is divided into two parts. First one, the basic concepts that are required to construct the compiler, which will be covered in the first semester. And the second part is how to use the basic concept in the to construct the compiler, which will be covered in the second semester. In the first semester, our first chapter is introduction. In this, we are going to define the languages. We will see operation on languages, and we will see how to represent a language using regular expression. Second chapter is finite automata, that is FA. So basically, whenever we study any language, say English language, Marathi language, or any programming language, we have to first of all study alphabets, then form the different words, and then arrange these words to form the sentences. In this chapter, we will see how to validate the correct words using finite automata. So here we will study the concept of finite automata, different types of finite automata, that is deterministic finite automata, non-deterministic finite automata, and non-deterministic finite automata with epsilon modes. Then we will see the construction of these different type of finite automata. Then the different conversion methods from one finite automata to another type of finite automata. Once the DFA are constructed, they can be minimized. It is similar to how we are minimizing the expression, mathematical expressions. Then we will see the finite automata with output, which can be used in different editors. Next chapter is regular language. It is relation between regular expression and finite automata. In this, we will study the conversion method between regular expression and finite automata. We will study different properties of regular languages, and we will study how to check whether the given language is regular language or not using pumping lemma. The fourth chapter is context-free grammar and languages. The finite automata only validate the different words. After getting the correct words, we have to arrange them using some rules, and these rules are given by the grammar. So in this chapter, we will see the basic concept of grammar, different types of grammar, then construction of context-free grammar, that is the CFG, then properties of context-free languages, that is CFL, simplification of CFGs. There are some normal forms of CFG. We will see these normal forms of CFGs. Then the relation between regular grammar and finite automata. Next chapter is push-down automata. The finite automata is having some restriction. It cannot accept all the languages. So to accept this new languages, we need machine, and that machine is the push-down automata. This machine uses the memory in the form of stack. Meaning of this is finite automata does not use any memory. In this chapter, we will study the basic concept of pushdown automata, different types of pushdown automata, how to construct the PDAs, and conversion method from CFG to PDA. Sixth chapter is Turing machine. PDAs are also having some limitations, and hence we need Turing machine. So in this chapter we will see the concept of Turing machine, construction of Turing machine as language recognizer, different types of Turing machine, different types of languages accepted by Turing machine, and the concept of linear bounded automata. This is the syllabus for first semester. Now before studying the topic from our syllabus, we have to revise some terminologies that already you have studied in the first and second year of BSc Computer Science. The first terminology is set. It is an unordered collection of elements without repetition. There are different ways to define set. The first one is listing method. In this, all the elements are enclosed within curly bracket and separated by comma. Second method is set builder notation. In this, a function is defined to represent all elements of sets. Third, statement form. In this, a statement is defined to represent all the elements of set. Fourth, recursion method. In this, a recursive formula is defined to represent all elements of set. Next terminology is cardinality of set. It gives the number of elements in the set. For example, if capital A contains the elements 1, 2, 3, then the cardinality of set is equal to 3. The cardinality of set is denoted by mod of A, that is, it is denoted by modulus operator. The next is types of set. There are two types of sets. The first one is finite set, in which the number of elements or members are countable. For example, capital A is equal to 1, 2, 3, 4, 5. That is, there are 5 elements in the set. Second is infinite set, in which the number of members are not countable. For example, capital A, that is the set, is equal to 1, 4, 9, 16, 25. So many elements. In short, you will observe that this is nothing but collection of squares of positive integer. Next terminology is set membership notation. Here, belongs to operator is used to represent set membership. For example, if A is equal to 1, 2, 3, then we say 2 belongs to A, that is 2 is member of A, and 7 does not belongs to A, that is 7 does not 7 is not member of set A. Next is subset. A set A is said to be subset of B if every element of A is also element of set B. For example, if capital A, that is the set A, is equal to 1, 2, 3, then all possible subsets are phi, that is the set with 0 number of element, then set with 1, set with 2, set with 3, that is the sets with a single element. Then the sets with 2 elements are the set with 1, 2, set with 1, 3, set with 2, 3, and the set with all elements, that is the 1, 2, 3. Proper subset. A set A is said to be proper subset of set B if and only if all elements of A are present in B and B is having one extra element. For example, A is equal to 1, 2, 3, then the proper subset is 1, 2. So you find that in the new set, element 3 is not present, which is present in the set A, and hence 1, 2 is the proper subset of set A. Next is equal set. Two sets are said to be equal set if and only if all elements from both the sets are equal. For example, if set A is equal to 1, 2, 3 and set B is equal to 3, 1, 2, then we say that set A is equal to set B because 1 is present in set A as well as set B, 2 is present in set A as well as set B, 3 is present in set A as well as set B. Observe here, the order of element does not matter. Now next terminology is empty set or null set. A set with no element is called as an empty set. It is denoted by phi. Next is the operation on sets. The first operation is union. It is collection of all elements from both the set without repetition. For example, capital A is equal to 1, 2, 3 and B is equal to 5, 2, 6. Then A union B will be equal to 1, 2, 3, 5, 6. Observe here, 2 is present in both the set, but we have written it at only once in the union set. Next operation is intersection. It is nothing but the set of common elements from both the sets. For example, if A is equal to 1, 2, 3 and B is equal to 5, 2, 6, here the common element is 2 and hence A intersection B is equal to 2. Next operation is set difference. It is nothing but collection of all elements from set A which are not present in set B. Okay. For example, if set A is equal to 1, 2, 3 and set B is equal to 5, 2, 6. Now here 2 is present in set B, so the A minus B will be found as 1, 3 only. Next operation is Cartesian product. It is the set of ordered pairs xy such that x always belongs to A and y always belongs to B. For example, if A is equal to 1, 2, 3 and B is equal to 5, 2, 6, then A cross B, that is A Cartesian product with B, will be found as consider one element from first set and one by one element from second set. Now here we will found the pairs as 1, 5, 1, 2, 1, 6. Similarly, we can find the pair by considering second element of the first set and one by one element from the second set. That is 2, 5, 2, 2, 2, 6. Similarly, we can find the pairs as 3, 5, 3, 2 and 3, 6. Next is power set of A, that is 2 raised to A. It is nothing but set of all possible subsets of A. For example, consider capital A is equal to 1, 2, 3, then 2 raised to A is equal to 5, set with 1, set with 2, set with 3, set with 1, 2, set with 1, 3, set with 2, 3, set with all elements, that is 1, 2, 3. Next is complement of set A. It is nothing but collection of all elements which are not present in the set A. Now next terminology is relation. It is collection of ordered pairs which defines an association between the elements of one or two sets. Remember here, when we write x r y means that the pair x comma y is in R and x r dash y means x comma y is not in R. For example, if A is equal to 2B is defined as a relation on the set of positive integers, then the ordered pairs within the relation can be found as 2, 1, 4, 2, 6, 3, 8, 4, and so on. Properties of relations. We say the relation is reflexive if A is related to A itself. If A is not related to A itself, then the relation is irreflexive. If A is related to B and B is also related to A, then we say that the relation is symmetric. If A is related to B and B is not related to A, then we say the relation is asymmetric. If A is related to B and B is related to C and also A is related to C, then we say that the relation is transitive. Next is equivalence relation. A relation R is called as equivalence relation if it is reflexive, symmetric, or transitive. For example, equal to relation is defined on the set of integers. Then we say that this is equal to relation is equivalence relation because we know that any integer a is equal to itself, and hence we say relation is reflexive. We know that if integer a is equal to integer b, then integer b is equal to integer a is also true. So the relation is symmetric. If integer a is equal to integer b and integer b is equal to integer c, then we know that in case of integers, integer a is equal to integer c is true, and hence the relation is transitive. As the relation is reflexive, symmetric, and transitive, the equal to relation is equivalence relation. Next terminology is closure properties of relation. If R is the relation on the set S and P is the set of properties of relation R, then P closure of relation R is the set of all pairs of R and all those new pairs which possesses the property in P. There are different types of closure. First one, reflexive closure. Second, symmetric closure. Third, transitive closure. Fourth, reflexive symmetric closure. Fifth, reflexive transitive closure. Sixth, symmetric transitive closure. Seventh, reflexive symmetric transitive closure. We will see the example how closure properties of the given relation is found. For example, if R is defined on the set of integers 1, 2, 3 as the collection of pairs 1, 2, 2, 4 and 4, 3. Then the first one, reflexive closure can be found by considering all the pairs from the relation that is 1, 2, 2, 4, 4, 3 and by adding the new pairs that gives or that satisfies the reflexive property that is 1, 1, 2, 2, 3, 4, 4. Symmetric closure can be found by again considering the given pairs from the relation and by adding the new pairs that satisfy the symmetric property. That is, as 1, 2 is in the relation, we can add 2, 1. 2, 4 is there in the relation, we can add 4, 2. 4, 3 is there in the relation, we can add 3, 4. Now transitive closure. To find it, again consider the pairs from the original relation and add the new pairs which satisfy the transitive property. Now here we can add 1, 4 because 1, 2 and 2, 4 is there in the relation. We can add 2, 3 because 2, 4 and 4, 3 is there in the relation. We can add 1, 3 because 1, 2 and 2, 3 is there in the relation. Next is reflexive transitive closure. It can be found again by considering all the pairs from the given relation and then by adding the reflexive properties that is 1, 1, 2, 2, 3, 3, 4, 4. Then add the pairs that satisfy transitive property that is 1, 4, 2, 3, 1, 4. In this way, we can find the remaining type of the closures for the given relation R. Now here we have seen the different terminologies that are used in the theoretical computer science. Now in the next lecture, we will start with the actual topics from actual syllabus.